Last year, term 2.
For what? Oh, okay.
Are you going to teach us?
Okay.
Yeah, you're going to have to hand it over eventually.
Streaming.
Hello! Hi.
We're good.
Your viewers. You can
Yay! I can relax. Alright. I won't stream, right? Okay. Hi everyone! Welcome back to those of you who are returning for 1141's help seminar. Today we're going to go through calculus, and essentially what we're going to be doing is looking through a bunch of problems and also kind of just going through a couple concepts. So we've got our first topic here, which is sets, inequalities, and functions. I'm sure this is revision to most of you. So essentially, hi, hello, come on in. So essentially what's going on here is we want to solve this kind of inequality, and we've got an absolute value. So I guess the first thing that I do whenever I'm looking at an absolute value, is I like to just think about the different cases where it's positive and negative, right? Because then we've got like a slightly more manipulable like algebraic expression. So what I'm going to do is I'm going to take two cases, just so it's easier to work with the expression inside the absolute value. So let's take the first case where the expression inside the absolute value is positive. This means we can just undo the absolute value because the value inside is already positive. So we get this, and then we get this, and then we get this. Okay, but there's one thing that we have to check after we've kind of reached this conclusion, which is quite crucial, which is that it satisfies kind of this initial condition that we're considering the case under. So here, essentially, I hope you'll agree with me that this is our condition. And I guess this is like, if we draw a number line, we've got 0 here, and then we've got like 514 here, and 2 is like bigger than 514. So like this condition does satisfy the previous condition that we did our case with, which is this condition. So then we have our next case, which is this. Oh, sorry, which is this. Minus 5 is greater than, less than or equal to 0. You can put this equal to case in kind of either one of them. It doesn't really matter. And basically we find that this is like the thing that we have to satisfy in the eventual answer that we get while we're plugging this into the equation. So because there's an absolute value and this value is negative, we've got to take a negative around the whole thing, right? So kind of this is what we get. And I hope you'll agree with me that this gives us 4x minus 5 is less than minus 3. Because I've just kind of like chucked this over to the other side and then chucked this over to that side. You can also think about it as like multiplying both sides by negative 1, which flips the inequality sign. So where we go from there is we get 4x is less than 2, which gives us x is less than 1 on 2. And now we check whether or not this kind of is agreeing with, sorry, it's kind of glitching. Okay, there we go. Now we check whether or not this final answer that we've gotten is agreeing with this initial condition, and it is. It fits our given range. So our answer is, if we're going to write it in set notation, we have x is an element of, so we first have this one, which is minus infinity to a half, and also 2 to infinity. And remember, we do round brackets because this is like not like greater than or equal to, it's just strictly greater than, so we don't include half and 2 as the values. Okay, so that's the first question, nice and simple. And we've got a written solution just here. Yeah, so that's kind of the value. If you want to, I guess, graph it out, we got 0, half, 2, and it kind of just looks like that. Okay? Yes? Sorry? Why do we take it's less than 0? So you mean, why do we do this step? Okay, so I went through this briefly while you weren't here, but basically we've got two cases that we want to work through, right? This is case 2 and this is case 1. So for the first case, we do that the thing inside is positive or 0. You can really do the 0 case in either case, but this is because our original equation is this. Minus 5 is less than, greater than 3. Yeah? So because there's an absolute value and we want to make this absolute value like easier to work with, what we want to do is we want to split it up into two cases. When we're taking the absolute value of some value, let's say just a, where a is like a real number, the absolute value of a is equal to a if a is greater than or equal to 0. Yeah? But the absolute value of a is equal to minus a if a is less than 0. Okay? So to work with this algebraically, what we want to do is we want to make it into something we can manipulate. So what we do is we take the two cases. Does that make sense?
Take the negative reciprocal of 4x minus 5, so it becomes negative 4x plus 5?
Yes, that's exactly what we're doing in the second case.
Oh.
Yeah, that's exactly what we've done here. Just as you've said, we've taken the negative because the thing inside is negative, so we're making the whole thing negative, such that the absolute value is positive. Does that make sense? Yeah. Okay. All right, let's look at limits. This is probably my favorite part of the course. So we're going to look at the Epsilon-M definition of a limit at infinity. A lot of words. Suppose that L is a real number and that f is a real valued function defined on some interval, b to infinity. We say that the limit of, we say that this is true if we're able to find a real number m for every positive real number epsilon, such that this condition, I guess, holds, this condition over here. I like to think of it, because I guess you have two ifs here, which can get a little bit confusing. I like to think of it as, you know, like for all positive epsilon, there exists, this is exactly like, literally exactly the same as the thing that's written above. There exists a real number m, such that I like to think of it as x is greater than m implies, just so we get rid of kind of that double if, you know, we've got an if here and an if here, just so we get rid of that confusion. I like to say, you know, this is true such that x is greater than m implies that this function is within epsilon of the limit value. So let's kind of think about this diagrammatically, if we're, you know, going to think about this a little more conceptually in terms of the actual definition. Let's say we've got 1 on x here, right? We've got y equals 1 on x here. And essentially what we've done is we've kind of like picked a point, right? I guess if we're thinking about this separate to this diagram with the other graphs in it, let's say we've got, so we want to like find an m for every epsilon such that this condition is true. So let's say we take epsilon equals to 1, you know, just for fun, let's have a look at kind of what our m value is when epsilon equals to 1. So our L value is equal to 0 if we're taking, you know, if we're trying to prove that, this is equal to 0. What this essentially means is that f x minus L, or 0, has to be within epsilon of the limit. So f of x has to be within epsilon of the limit. So essentially what's going on here is we've got 1 here, and we want to be like 1 within, you know, 0, which is our ultimate limit value. We want to be 1 within that, and if we're to the right of x equals to 1, then we do kind of fit this, restriction that we've given here, which means that x is greater than 1 implies that f of x minus L, or 0, is less than 1, where this is our epsilon value and this is our m value. So here we've succeeded in finding an m value, basically, which allows us to make this conclusion. And we just have to do that with every single other epsilon value that exists on the positive real line, but obviously we don't have the time to do that. So what we're going to do is we're going to find m in terms of epsilon so that we prove that there's an m which exists for every epsilon value, which is positive. So kind of let's have a look at this problem just to put this in action. Use the Epsilon-M definition of the limit to prove that, you know, the limit of this expression is 1. So I guess the very first thing I'm going to do is I'm going to let f of x be kind of this function, just so, you know, for conciseness. And essentially what we're going to do is we're trying to prove that L is 1 and that L being 1 satisfies kind of this condition up the top. So the next thing we're going to do is we're going to consider this value. So f of x minus L, which is x squared minus 2 on x squared plus 3 minus 1. And, you know, if you do some algebraic manipulation, I hope you'll agree with me that this is just minus 5 on x squared plus 3, absolute value. So because this is an absolute value, and we know that the bottom is, you know, it's always positive because x squared is always positive. I guess it's always positive, not even 0. We know that x squared is always positive, so the bottom is positive, and the top is negative, which means that we can just rewrite this as this, and we know that this is a value which will always be positive, so we can just simplify it in that way. Essentially what we want to do is we want to kind of get this to some form of like an equation, right? Because remember that the property, or sorry, the outcome that we're working with is f is the absolute value of f of x minus L is less than an epsilon value. So we want to find some kind of an epsilon value in terms of x that it's like less than. And I guess here, if we want to make the algebra a little bit easier, it's very convenient. You know, we know that x squared plus 3 is greater than x squared, which means 1 on x squared plus 3 is less than 1 on x squared, which means that we can have this property that our f of x minus L absolute value is smaller than this expression here. So I hope you can agree with me that that's just a consequence of, you know, this property right here. Okay, so essentially what we're going to do afterwards is we're going to let 5 on x squared be smaller than our epsilon value. Yeah, because if that's true, then we have found kind of an epsilon which is always greater than this value, or in other words, we've proven that this value with the absolute value is smaller than our epsilon. So what we're going to do is we're going to set epsilon to be like that, and what we're going to do afterwards is this. We know that this is true if this is true, I guess. This is true if and only if this is true. So essentially all I've done is just algebraic manipulation to get from here to here. You know, multiply over x squared. X squared is positive, so we can do that, and then take square root of both sides. Square root's an increasing function, so we're allowed to do that once again. So this will only be true if and only if this is true. So essentially what we've done by doing this is we found some kind of a condition which is necessary for, we found a condition which is sufficient to say that f of x minus 1 is less than an epsilon. And this condition is x is greater than the square root of 5 on epsilon. Okay, so essentially this is the statement that we've now derived. And that's very convenient for us because then we can just let m be square root of 5 on epsilon. And if you look at the kind of original statement, or the original definition of an Epsilon-M limit, you'll notice that the motivation behind setting this as m is essentially just to match up this statement that we've derived with the original definition. So by allowing m to be square root of 5 on epsilon, what we've done is we've found an m value that exists for every epsilon. So as long as epsilon is a positive real value, which it always will be, there will be an m which exists. So therefore what that means is that L equals 1 fits the definition as required. So essentially what's going on here is that we've found one m value such that this statement holds true, this statement up here holds true for every value of epsilon. And instead of testing out every single epsilon, we've done this in quite an efficient way, just by finding m as an expression of epsilon. So for whatever epsilon, there will be an m, which is in this form down here. Okay, and essentially that's exactly what our answers have given us. So we let L be 1, we find something which is greater than it always, which is this expression. We consider an epsilon value, which is greater than that expression, like this. And then we derive an x value. And then we derive an m value based on our x. So this becomes our m value, and after that we win. We've basically proven that L equals 1 satisfies the Epsilon-M definition of the limit. Okay, hopefully that was making sense. So now I'm going to go on to kind of use some properties of limits just to evaluate a limit. Nothing fancy here. Essentially what we're doing is we're just trying to find a numeric value for this. And I guess the very first thing that I'm going to do, my intuition tells me that I should split this. Yeah, so I can kind of do this. Just so that it's a little bit easier to work with. And because we've kind of got this property that you know, we've got this property, I'm sure you've seen it before. If we've got f of x plus g of x, we can kind of take this outside, right? We can make this the limit as x approaches a for f of x plus, you know, the limit of x approaches a for g of x. Again, you can prove this using, you can actually prove this using the epsilon delta definition of the limit, but I'm not going to go over that today. We're kind of just going to have to take this for true, I guess. So what we've done is essentially we've just split this up into two parts. Yeah, nice and simple, nothing too fancy. And then what we do later is we realize that this is a constant. So this constant is independent of where x approaches or what x is doing. So this is always going to be 3. And if we look at this, it kind of reminds us a little bit of some limit identity that we've seen before. And that limit identity is probably no stranger to a lot of us. It's the limit as x approaches 0 for sine, I'm going to say sine theta over theta. And this is 1. Yep, so we're allowed to kind of just use this property of sine theta over theta. And it still looks like a little bit different. Like we've got kind of, you know, we've got different things in the sign and on the bottom. So what we want to do is we want to make it look more like the thing that we have in blue, which is our known property. So what we want to do is we want to do this. We want to do limit as x approaches to 0 for sine. It's easier to manipulate the bottom than it is to manipulate what's inside the sign. So what we're going to do is we're going to manipulate the denominator so that it looks exactly the same as the thing which is inside the sign. But we don't want to change our fraction. So what we want to do is we want to just, you know, get rid of this. So essentially what we've done is we've just times by 1, we've times by 2x squared on 2x squared. So the fraction itself hasn't changed at all, but this has become a much easier form that we can work with, which is 2, you know, from cancelling the limit, to limit as x approaches to 0, sine 2x squared over 2x squared. And I hope you can agree with me that this is, and this are essentially in the same form. So we can say that it's 1. I guess if you really want to be very rigorous about it, you know, this, oh, sorry, this should be theta. Didn't see that there. Should be theta, not x. X is not relevant to this at all, but yeah, should be theta as approaches to 0. If we want to be really rigorous about this, over here, I guess we should say that this is 2x squared approaching 0. And I guess they're the same thing, because if x approaches to 0, 2x squared also approaches to 0. So now we've kind of gotten this in the form up here, so we're allowed to apply it. So what we can do is we can just do 2 times 1. Yep, so altogether, essentially what we've done is we've found that this part of our limit is 3, and this part of our limit is 2, or 2 times 1. So altogether what we've got is we've got 3 plus 2, which is just 5. So our final answer with all that manipulation is 5, and as you can see in the answers below, that's essentially exactly what's happening, except I think they've, you know, missed the limit there, but that's okay. Okay, so I guess there's also another way that you can sort of think about how to approach this problem. Does anyone actually have any ideas? I'm interested to see if there's any other ideas in the audience. Okay, well, this is going to be covered by Rashid later on with under mean value theorem, but we can also approach this with something that's called L'Hopital's. Gasp, yes, I know, very exciting. Rashid's going to cover what this is in a bit, but I'm not going to spoil his thunder, and I'm just going to put that out there for now. You can also solve this using L'Hopital's. Okay, so that's that for limits and Epsilon-M and all of that jazz. We're going to now move on to continuous functions, and I guess the definition that we're encountering with continuous functions is a little bit, or I guess noticeably different to the definition that we come across in high school, which is probably, oh, you know, like you can draw the curve without lifting your pen off the page, but this is actually the rigorous and proper definition of continuity. So the definition for continuity is actually derived off of the definition of a limit, or the concept of a limit, and essentially what it means is that something like let's say this, something like let's say that would not be considered as something which is continuous, because our f of a value is here, but, and your lecturer has probably stressed this, the value of your limit has nothing to do with how your function actually behaves at the point x equals a. So let's say this is a. If we call this value, I guess, c, then what's actually happening is that the limit as x approaches to a of f of x is not f of a, it's c, because we evaluate this limit at a point from the left-hand side, and the right-hand side, and because they're equal and they're both equal to c, we can say that this is true. So the value of the limit has nothing to do with this point. If it was related, then this definition of continuity would be quite redundant, but they're not related, so it's a special property that if this is true, then that means that the function is continuous at this point. Okay? All right, so let's have kind of a look at some things which we can conclude off of a continuous function. I guess the first one is the intermediate value theorem, which is really quite intuitive of a theorem, but I think it's still quite good to put it in mathematical writing. Essentially what it's saying is that if we have a closed interval AB, if Z lies between f of A and f of B, which is like these two values that correspond to the endpoints, the y values of the endpoints, if Z is kind of just like, anywhere in between here, then that means that there exists at least one real number C in this interval, in this x interval, such that f of c is equal to z. We have to know that the wording here is, the wording here is at least one, yeah? So not one exactly, but at least one. So there can be 1, there can be 2, there can be 75, I guess, if there are. Here in this example that we've been given, there are 3, yeah? So f of c1 is equal to f of c2 is equal to f of c3, which is equal to z here. That's what's happening here. And this is kind of just to show you that the intermediate value theorem does not tell you that there is a unique number c, or there's just one value which this satisfies. It can be multiple values, and here we've got 3. Okay, that's that for this. All right. Okay, now let's kind of look at some applications of intermediate value theorem, and also, I guess, think a little bit about the ways that we can use this in a problem. Okay, so the first question is, we want to know what the maximal domain of A is a proper subset of R is. So essentially what we're doing is we need to analyze this function and think about all the things which are X that we could, I guess, plug into this function without, something strange happening. And I guess the most salient thing to me is the fact that there is a ln function, or ln, or natural log, however you want to say it. But there's a log function here, and one striking property is that ln of x can't take in any values which are negative or 0. So it can only take in positive values. So what that means is essentially that this thing that is inside our log has to be positive. Yeah? So this property of ln, which is that it can't intake, anything which is negative or 0, informs what our maximal domain is. So I guess the next thing that we're going to do from here is we're going to consider top and bottom. And so I would intuitively kind of think of what's on the bottom first, because it's got pretty clear or pretty obvious bounds. Cosine is bounded between -1 and 1, and if we add 2 to that, then we'll bound it between 2 positive values, essentially. Yeah? So what's on the bottom is always going to be positive, so this is always going to be positive. We don't have to worry about that at all when we're considering our domain. However, what we do have to worry about is what's on the top. We have to make sure what's on the top is also positive. So because this is positive, as we've proven that here, what we have to do now is we have to prove that what's on the top is also positive. Oh, sorry, we have to find a value of x such that what's on the top is also positive. So I guess I'm gonna relocate here. So what we're trying to solve for is x when this is positive. Yep. So I guess what we do is just some, nice algebraic manipulation. 1 on 2, take the log of both sides. We get x is greater than ln of a half, which is minus ln2. So that's essentially our maximal domain. There's nothing else that we have to consider in this function which could go wrong. It's mainly just making sure that whatever's inside the log function is positive. So if we want to write our domain in, I guess, set notation, then what we do is we do this. Our domain is x is in, well, we have this, so I guess 0, negative ln2, and it's going to be bigger. So minus ln2, infinity. Or alternatively, you could also write it like this, I guess, because A is a set, and this is an interval, which is a set of points. Okay, nice. So we've kind of derived this domain of this function, and that's the maximal domain, and we know that because the function can't take on any values that are outside of this domain. And that's essentially what's happening here. So just to sum up the proof, we've considered how cosine is bounded, then we've considered the fact that it's always going to be positive and non-zero, then we've considered the top of the fraction, which is 2e to the x minus 1. And we've used kind of that part of the fraction as something positive to derive this, which is our maximal domain. So the next part of the question is actually the more interesting part, where we're using intermediate value theorem to, I guess, explain why there is some value c in this maximal domain where f of c is equal to 1. And kind of, you know, apart from the fact that they literally tell you to use intermediate value theorem, there's a lot of things which, about this question, you know, are very characteristic of an intermediate value theorem question. They've basically said you want to prove the existence of some c in A. You don't need to prove that it's the only one, but you need to prove that, you know, there exists some c in A such that this is true. So I guess with intermediate value theorem comes a little bit of trial and error. You want to be kind of trialing and erroring what your possible A and B values could be. Yeah? And the desired outcome is to find some f of A and some f of B such that one lies between these two values. And I guess we could spend quite a long time, I guess, drawing up tables and things like that with x and f of x, but I'll kind of just spoil it for everybody. We want to consider f of 0, I guess, quite intuitively, because it's, you know, I guess just quite an obvious thing to consider. F of 0 is 0. Yeah, so f of 0 is 0 because the top is 2e to the 0 minus 1. The bottom is 2 plus cosine pi, which is just 2 minus 1, 2 minus 1, which is just 1. And when we log that, we get 0. So f of 0 is 0. And then what we would do afterwards is, I guess we can maybe go up and see whether or not there's anything, you know, above 0 or below 0 where the f value is more than 1, because we've currently got something which is less than 1. Let's try f of 1. So I guess if you plug this value into your calculator, you'll get that it's roughly equal to like 1.112 something or other. Yeah, and that's greater than 1. So essentially what we've done here is, we don't really know how the curve behaves between 0 and 1 as x values. Like if we have 0 here and 1 here, we don't really know how the curve behaves. It could be like doing this or whatever. But what we do know is that it will cross at least once from, if we have this as 1, it will cross at least once over y equals 1. So it'll do that at least once. Like I said, it could be doing this or like, you know, this or whatever. But from the intermediate value theorem, because this function is continuous, what we know is that it will cross over here at least once. So I guess between 0 and 1, there exists some c where f of c is equal to 1. I'm just going to write that up. There exists some c in 0 and 1 such that this is true. So I guess the last thing that we have to verify is that this interval 0, 1 is actually within A, which is the maximal domain that we've defined. And it is, which is very helpful for us. So if I just draw it out again, the maximal domain that we've defined is from negative ln of 2 to infinity. Yeah? So the values that we've picked are 0 and 1, which are both, thankfully, within A. So there must exist a C. So I guess the thing that we can conclude is that there must exist a C in A such that this is true. So we've proven that with the intermediate value theorem, and I guess that's all fine and good. There's just kind of one small thing that I would additionally include at the top of my proof, or you know, somewhere which I guess is relevant. Probably the top of my proof is the fact that one kind of key condition of the intermediate value theorem is that f of x has to be continuous on this closed interval. So we haven't actually proven that f of x is continuous, but I guess it's sufficient to kind of say that it is an elementary function. And all elementary functions are continuous. It's an elementary function because it's composed of a bunch of different operations with the logs, the exponentials, the trig functions, the algebra functions, roots, and whatnot. That makes it an elementary function, which makes it continuous over its natural domain. And that's the maximal domain that we found in part A. So it's elementary, therefore it's continuous. Yeah? Okay. And that lets us use intermediate value theorem. All is good and well, and we've proven the thing that we want to prove at the very end. So I guess here is the explanation in words. We found two values. We found an A value and we found a B value, and we've applied intermediate value theorem. All right, now let's look at differentiable functions. This is kind of the next part, and we build differentiability kind of on top of continuity, which we built on top of limits. So there's kind of this nice layering that's going on to what we're learning. And I guess the very first thing I want to do before I even dive into this question is talk about the definition of differentiability. So we have this thing which is called the difference quotient, which looks a bit like this. And essentially something, I might replace this with like A. Yeah, might replace this with A. As we take the limit as h approaches 0, if this is an existing value, then we say that f of x is differentiable, I'm just going to say diffable, at x equals a, if this kind of thing exists. And if it exists, then we can call it f dash of a. Same with, I guess, x. If this difference quotient exists with a as x, you just replace a with x, then we say that f dash x exists, and we call this thing the derivative. Okay? So essentially what we're doing here is we're trying to, if you read the question, consider the function, and you've been given this kind of piecewise function. You've got to make it a differentiable function by picking a value of a, essentially. So this is actually secretly two questions to some extent, but we'll go over that in a bit. Let's kind of focus on what's at hand first. We want to make sure that h, the function, is differentiable. And I guess the very first thing that I want to do is I want to think about the derivatives of both of these parts. So if you want to rigorously rigorously derive your derivative, I guess you can go from first principles if you really want, but I'm sure you'll agree with me that when you diff that, or when you diff both of these things, you'll get 2ax plus 3 and 2. Essentially, nothing really different that you've seen in high school. This is pretty much exactly the same as what you've seen in high school. So, like I said, if something is differentiable at this point, then that means that it's kind of left-hand, like the derivative on like the left-hand side of 1 and the derivative on the right-hand side of 1 have to kind of agree. So as we're, moving from 1 plus, we'll be kind of in this domain, and as we're moving from 1 minus, we'll be in that domain. So what we want to occur is we want the derivatives from kind of both of these domains to coincide and be the same value. So that's good because, we've got kind of the values of the derivatives here, which means that the limit as x approaches to 1 minus, or from the left-hand side, of h of x, h dash x, is equal to, we sub that in here, it's just 2. Whereas if we're going from the right-hand side, I'm not going to write it out again, but if we're going from the right-hand side, what we get is 2a times 1 plus 3, and we get that from here. We're going from the right-hand side because x is greater than or equal to 1, so we pay attention to the first branch of this function. So what we've got is we've got 2a plus 3 equals 2, 2a equals minus 1, so a is equal to minus a half. We need to find b as well, and I guess it kind of looks like our job is already done because we've, considered differentiability. But one important thing that you have to note is that differentiability implies continuity. So this is something that's quite important. So you also have to make sure this function is continuous, because if it's not continuous, then there's every chance that we've just got something like this. that's like one example of, I guess, something where the derivatives match up on either side, but the values kind of like aren't matching up. So it's not differentiable, because if something is differentiable, it also has to be continuous at that point. That's for reasons that you can derive from this difference quotient kind of definition of differentiability. You can kind of push from this, to this. Yeah, which is equivalent to this. So yeah, essentially proving this means that you've proved this, and because we can prove this with the difference quotient, we can prove that wherever something is differentiable, it also must be continuous. That's the definition of continuity that we looked at before. So how do we prove that, how do we find a value of b such that these two branches kind of will match up and so that the function will be continuous? What we do is we essentially just equate the right-hand side limit and the left-hand side limit. So what we want is this. We want the limit as x approaches to 1 minus h of x to be equal to the lim of x approaches 1 plus h of x. We want them to be equal. Yeah? And essentially what this is when we're approaching from the left-hand side, exactly the same as we did with the derivative, we have to pay attention to, I'm just going to rub all that out, we have to pay attention to this branch, right? So it's 2x plus b here. Whereas if we're approaching from the right-hand side, we're approaching from this branch. So it's ax squared plus 3x. And I hope you'll agree with me that when we kind of move the x values inside, we'll get 2, 1 plus b is equal to a 1 plus 3, 1, which leaves us with, b is equal to a plus 1. And because we've got our a value here, we can kind of just plug that in and we'll get b is equal to a half. So one kind of key takeaway from this question is that if a function is differentiable, it has to be continuous, which means we have to satisfy both differentiability and continuity at that point. And that's kind of the only way that we can get kind of these two values, which make h differentiable at x equal to 1. So our final answer is a is equal to -half and b is equal to half. Okay, and that's kind of exactly what the answers have in mind as well.
So we use 1 for both of them.
Sorry?
Why do we equate them?
Where?
For like the top, you said we want to equate them. Why do we equate them?
What is them?
It's like the limit of the left hand side to the limit of the right hand side.
Here? You mean here?
Yeah.
Okay, so if you remember the definition of continuity, continuity is defined at a point with two limits, the left-hand side limit and the right-hand side limit. So if we have a function which is, for example, something like this, let's say, let's call this value kind of a, let's call this f of a, because this is the actual function value, that little dot that's over there, that's the actual function value. And let's call this, just erase that. And let's call this like c or something, okay? So the limit as x approaches to a of f of x, if we call that function f of x, we're kind of approaching from, so the condition for this to exist is that this must equal to this. Oh, I can't pinch. This must equal to this, and they must both be an existing value, which means that the function can't oscillate wildly at that point. The function can't go to infinity at that point. It can't go to negative infinity at that point. It has to be like a real value. If both of these, which is when we approach from the left-hand side and when we approach from the right-hand side, if they kind of approach the same value, which is also a real value, then we say that f of x is continuous. Sorry, yeah, f of x is has a limit at that point, not is continuous, has a limit at that point. So continuity, if you remember, is defined as this. This is the definition of continuity, yeah? So one prerequisite of continuity is that the limit has to exist at that point, yeah? And for the limit to exist, we have to satisfy this property.
You could use the formulas, but can't you just do how you
when we found A, what we did was we took the derivative of both sides, right? Sorry, not both sides, both branches of the equation. When you take the derivative of a constant like B, it vanishes into thin air. It goes to zero, essentially. So after we've taken the derivative, we can't essentially work with B anymore. We can still work with A because A is the coefficient of something which has got an X attached to it. So A doesn't vanish into thin air. But when we take the derivative, B vanishes into thin air. So essentially what that means is that we have to find B through the means of continuity. And lucky for us, differentiability implies two things. It implies obviously that the derivative is like continuous, or that, you know, from the left-hand side and the right-hand side, the derivative is the same value. But it also implies that from the left-hand side and from the right-hand side, the function value is also the same and that it's continuous at that point. So you've got to use both of those properties to find A and B. If you just use differentiability, your B vanishes into thin air because you've, you know, differentiated and it's just run off like a constant would. Whereas, you know, if you use continuity, you're able to kind of work with B, and you're also able to engage with the property of differentiability, that if something is differentiable at a point, it's also continuous at that point. Okay, so that's pretty much it for my section. This is, you know, I guess, continuity. And I hope you'll agree with me that this is not continuous, this function. This is just like a separate example that's not relevant to the question at all, but that's kind of just to, you know, get you to understand that this is how continuity is derived from limits, and that for something to be continuous, the limit has to exist from the left-hand side and the right-hand side, and they have to be the same thing. So that's like a prerequisite of continuity, which is this limit existing and being equal to the function value. So here it's not equal to the function value, which means that it's not continuous. Okay, that's essentially all I've got for differentiable functions. So we're moving on to the mean value theorem now, and I'll hand over to Rashid. The mic is a little bit...
Oh, we have one of those now.
Yeah, we have one of those now.
Yeah.
Oh gosh. It's like kind of...
Is this yours?
Yeah, that's fine. Oh no, he's yeah.
So there's 3 MathSocs here, there's 2.
Yeah, but it's online. That's like the main platform. You go.
Yeah, behave yourselves, because we outnumber you.
Yes. Is this yours? Or is this yes.
That's mine. Hello, everyone. Round of applause to Angie Wang. The lovely opening to the calculus part of the revision seminar. All right, now we move on to the mean value theorem. So this is really when we start reaching territory that we haven't covered in high school. The mean value theorem is described in Wikipedia as one of the most important results in real analysis. So, you know, this is one of the, this is one of the big fellas. This is one of the main characters of the calculus component. But if you think about it, then what it says isn't actually that complicated. All right. So if I draw this out, what it's actually saying, we've got, here are axes, right? And we've got this function f, right? And here's the function of f at A. Here's the function of f at B, okay? And what this left-hand side is telling us is it's just quantifying the rise over run across that interval, right? So that part of the top there, fb minus fa, that's just how much the function changes over that interval, right? This is fb minus fa. And that part at the bottom is just the length of the interval from B to A, that length, right? So that fraction is just telling us the slope of this secant. That's a pretty sloppy straight line, but it's telling us the slope of this straight line, okay? And what the right-hand side is telling us is that there is some mystery number c on this interval where the derivative is equal to the slope of that gradient, right? The slope of that secant. So in this case, I think that point C would be around there because the derivative at that point looks a little like this. We would have this gradient, and that's basically the same gradient as our secant, right? So that would be our point C. And the mean value theorem tells us that on any continuous function that's differentiable across this interval, there is always going to be this point C between A and B where the derivative is equal to the slope of the secant, okay? So when you draw it out like that, it's not that complicated. It makes sense, right? But the mean value theorem does actually become very useful when you're doing questions like this. All right, so let's read it out. Assume that a differentiable function f on R is such that the derivative of f is less than 1 for all x. Given that f of 2 equals 2, show that f of x is larger than or equal to x for all x is smaller than or equal to 2. All right, so one thing to note, a few things to know about this question is that we've got inequalities. We're going to be proving something that has an inequality in it. And also, we're given information about the derivative of the function. And usually, that should set off alarm bells that we're going to be using the MVT, the mean value theorem, right? Because that's what it's perfect for. When we're given information about the derivative and we're proving an inequality, usually that means that we're going to be using the MVT. So let's see how we actually apply it. The first step is going to be finding the interval that we're going to be applying it across, right? Our AB. What are our AB going to be? Well, a good choice for this is having the top one being 2, because we're working with x smaller than 2, and the bottom one being x, because we need to prove something about f of x, right? And that's exactly what we do. Here we go. Consider the interval x to 2, and we're given that the function is continuous on this interval and differentiable on the closed interval x to 2, and thus f satisfies the conditions of the mean value theorem, right? If you remember, the conditions for actually applying the mean value theorem is that the function is continuous on this interval, right? And that it has a derivative at all those points, right? Otherwise, you could have something like a function like this, for instance, that has a straight line going like this and a straight line going like this. There is no point along that graph that has a derivative that's equal to the gradient of this secant, right? If this is a and b. Because we've got this point here that doesn't actually have a derivative, right? That's why we have those conditions. So our function f does satisfy those conditions, so we can apply the mean value theorem. We plug in our b and our a, which is 2 and x, right? And we've got 2 and x here, and that's equal to the derivative of some point at some point c along the graph, right? And we know that this derivative c is going to be less than, or is going to be, was it less than? Yeah, less than or equal to 1, right? That's what we're given here. So we can say that this that this right-hand side is going to be less than or equal to 1. And then just using some algebraic manipulation, we get pretty easily that f of x is larger than or equal to x for x smaller than 2, right? Because remember, we started off with x being smaller than 2 when we chose this interval. If you want to be rigorous about it, we were asked to prove for all x smaller than or equal to 2, so you might have to mention later on in your argument that it also holds for x being equal to 2. But this is the basic structure of the argument that you're going to be using. All right, now on to other things that the mean value theorem is useful for. It is actually what we use to prove this interesting identity called the L'Hopital's rule. Okay, it's probably the hardest thing that you're going to have to pronounce in this course, and it's a rule for taking derivatives of fractions like this, right? So you're going to come across in the course functions that look like this, that look like some function divided by some other function, but when you try to take the limit of this fraction, right, say it's a limit from x to a, you find that it actually goes to 0 over 0 or infinity over infinity, right? And obviously that's no real answer. You can't write that down. So you need some other method to determine what this limit is. And L'Hopital's rule tells you how to do this, okay? So the conditions are this. If you've got this fraction, right, that you're trying to take the limit of, if either both f of x and g of x go to 0 at that limit, or both f of x and g of x go to infinity at that limit, then, and also as a third condition, if this limit exists, so the derivative of f over the derivative of g, then you can apply the L'Hopital's rule to get this identity, right? This limit is equal to this limit. The limit of the function over the second function is the limit of the derivative of the function over the derivative of the second function, right? And we're not going to go into how to prove this with the mean value theorem, but if you want some intuition for why this is actually the case, if you have, for instance, these two functions, let's have some colors. Black function, and at some point it goes to 0, right? And red function, at some point it goes to 0, right? If you're trying to take the limit of the ratio of those two functions at that point, then you know, a simplistic way of doing it would just be to take the value of this function really close to that point, right? So I'll call this delta f, right? And the value of the bottom function, right, really close to that point as well, delta g, and find that ratio, right? But what you'll find is that this is actually equal, right, to this ratio, right? Delta f over delta x, delta g over delta x, right? Which is basically a primitive way of denoting the derivative of those functions at that point, right? So basically this primitive technique of taking function values really close to the point where they go to 0 actually yields L'Hopital's rule, right? Because you're just taking these tiny slivers, right? These tiny intervals of the function really close to the point where they go to 0. All right, but that's kind of besides the point. The point is that if you've got this fraction that satisfies either this or this and this, then you can apply L'Hopital's rule to find the derivative. So let's see how you actually apply this, okay? So we've got this limit that we're trying to evaluate. Let's have a go at just doing it normally, right? So if you try to sub in 0, then you're going to get e to the power of minus 1 over 0 over 0. We've got a whole 2 zeros in denominators in that expression, so it's really, really bad, okay? Obviously, we can't take the limit like that. So maybe it's time to apply L'Hopital's rule to this fraction, right? We do have to check that it does actually satisfy the conditions, right? The top part, as h goes to 0, goes to e to the minus 1 over 0. No, I'll clean this up a little bit. E to the minus 1 over 0, which is e to the minus infinity, which goes to 0, right? And obviously the bottom goes to 0, okay? So we did satisfy one of our conditions. One of our conditions was that both of them go to 0, okay? And now we can try taking the derivative of both the top and bottom and seeing whether that limit exists, right? So if we do this, then what we get is actually a really bad looking expression that looks a little bit like this, okay? That's the derivative of the top, and this is what you would get, okay? Now, obviously, this is even worse than what we had before, right? So L'Hopital's being applied in this way did not actually help us at all, okay? Because we've still got the minus 1 over h squared in the power of e, and we've got an even bigger polynomial at the bottom, okay? Did not help us at all. But we do actually apply L'Hopital's rule to solve this question, just in a different way, okay? So what we start with is just by rearranging the fraction, okay? What happened here is that we turned this fraction, what you can think about, a way of thinking about what happened here is that we divided the top by this value, okay? h times e to the minus 1 over h squared, right? And we divided the bottom by that value as well. Gets quite messy, but what it simplifies to is 1 over h at the top and e to the 1 over h squared at the bottom, okay? And it turns out that when we apply L'Hopital's rule to this fraction, which is equivalent, okay, to this fraction, it actually behaves much better. So what happens is that at the top, we'll get minus 1 over h squared. At the bottom, we'll get minus 2 over h cubed times e to the, oh boy, times, my apologies, times e to the 1 over h squared, right? And when you simplify that, you just get h over e to the 1 over h squared, and the top goes to 0 as h goes to 0, the bottom goes to infinity as h goes to 0, and that's a much easier limit to evaluate. That just turns out to be 0, okay? So L'Hopital's rule did help us in the end. All right, but what was the second part of this question, okay? Subsequently determine whether this function is differentiable at x equals 0, okay? So if you recall what Angie explained to us earlier, if something is differentiable, that means it's continuous, in this case at x equals 0, and the derivative exists at x equals 0. It has a derivative at x equals 0. That's what it means to be differentiable at x equals 0. At x equals 0 exists. Okay. So, let's get started. First, we have to check continuity. Again, it's what Angie explained to us about continuity. We need to check if the right-hand limit and the left-hand limit and the function value at 0 align, okay? This is pretty easy. The limit of this as x goes to 0 would be e to the negative infinity, which is just 0, which is equal to our function value at 0 because it's defined to be 0, okay? And the same goes for the limit from the positive side of 0, okay? They're both equal to the function value at that point, so it is continuous. Our first criterion was satisfied. It is continuous, okay, at x equals 0. Now we need to check if the derivative exists at x equals 0, and we do that from first principles, okay? So we substitute in our x into this definition of the derivative, and we find that the limit that we end up with is the one that we solved before, right? So we can just paste in our answer from that, which is 0, right? And so the derivative at that point is actually defined, and it's 0, okay? So it is differentiable at x equals 0. Any questions so far? Yeah?
So when you have to check the limits of both equations, they have to be the same thing, right?
Yeah, they do have to be the same thing,
So
okay?
if they aren't, so if it's like, let's say we check the first time, right? It's like infinity over 0. That's therefore the L'Hopital rule.
Yeah. So if your fraction, as you take it out to your limit, equals infinity over 0, then do not apply L'Hopital's rule. First of all, because it's not intended for this case, but second of all, because you don't need to apply L'Hopital's rule, right? If your top is getting bigger and your bottom is getting smaller, then it's just going to go to infinity, right? So that's one of the good parts about a fraction like this. It will just go to infinity. But you will find cases, for instance, where, you know, we've got the bottom going to 0 and the top going to some constant, okay, to some c, then you would not be able to apply L'Hopital's. You would have to do something else.
Both of the numbers can be infinity, right?
Both of the numbers can be infinity. Yeah, that's right. Yeah, in our case, both the top and bottom went to 0. Actually, no. So this equivalent fraction that we got here, right? If you take 1 over h take the limit of that as h goes to 0, right? That obviously goes to 1 over 0, which goes to infinity, right? And if you take the bottom as h goes to 0, that would be e to the 1 over 0, which is e to the infinity, which is infinity over infinity, right? So when we actually did that algebraic manipulation to our original limit, we got an equivalent one that was of the form infinity over infinity, right? So you can apply it to both, yeah. But it has to be the same thing on the top and bottom. Okay, so that's it for mean value theorem for now, okay? Now on to some theorems involving inverse functions, okay? So here's the first theorem. Suppose that f is a one-to-one function, then the inverse of f will be a unique function denoted f to the power of minus 1, where the range of this inverse is a domain of f, okay? This should be pretty intuitive, okay? So if you have a graph of our function f, right? Right? If this is the domain of f, right? Then obviously the only outputs that our inverse function could give would be within that range, okay? Because what the inverse function actually does is it takes an output of f and it converts it back into an input of f, right? So obviously it can only be within that space. And what else do we have? Suppose I is an open interval and the function from I to r is differentiable and the derivative of f does not equal 0 for all x in that interval. Then we have that f is a one-to-one and has an inverse function, okay? So this function will go from the range of f to the domain of f, okay? Another way you can think about it, if you've seen diagrams like this before, right? This is the domain of f. This is the range of f, right? Our function f takes elements from the domain and maps them to elements in the range, okay? But our inverse function does the opposite of that. It reverses all of these arrows, okay? And that means obviously that its domain would be this, the range of f, and its range would be the domain of f, this bubble here, right? This is what f minus 1 does. Okay. Now, an interesting property about the derivative of the inverse, okay, is that it actually satisfies this identity. And there's different ways to actually arrive at this result. One way is algebraic. So if you have, for instance, you define y to be our inverse, g of x, then you would have that x is equal to the function of y, okay? Because they're opposites of each other. Then if you differentiate with respect to x on this side, you would get dy over dx is derivative of g. And on this side, if you differentiate with respect to y, you would get dx over dy is equal to the derivative of f at that point, okay? So you can see that this side and this side, they're just reciprocals of each other. So we can rewrite, derivative of g as 1 over f dash of y, and we know that y is a g of x, so you can substitute that in, you get exactly what we were looking for, f dash of g of x, right? So that's a purely algebraic way of arriving at this result. There are other ways as well, right? So, this is just a rewriting of the same result, except g is rewritten as, inverse f to the minus 1. If you want a more graphical way of looking at it, here are our axes. Here's our function f, okay? Our derivative, the derivative of f at this point x, right, is equal to whatever the rise over run is of the graph at that point. Okay, so the little change in y that you get per little change in x. Okay, but the derivative of the inverse function, which maps an output to an input, asks the opposite, right? It asks, what little change in x do I get per little change in y? And the answer would actually be the same, because you bump y in this direction, then your x would actually move the same amount. And this derivative of, the derivative of the inverse in that case would be just the inverse, I'll have y here, just the inverse of the reciprocal, of the derivative of the function at that point. Okay? And we can actually use this result to infer things about the derivative of the inverse at certain points on the function. Okay? So let's have a look at this question. We're given this function from the interval 0 to 2 pi to r. The function is x squared plus cosine of x squared. Okay, first part of the question, find all critical points of f and determine their nature. All right, so obviously we're just looking for the points where the derivative of x is equal to 0 or undefined. But in this case, there's not going to be any points like that, right? We don't have any absolute values in that function. We should be fine. So let's solve derivative of x equals 0. Derivative of f equals 0, sorry. The derivative actually ends up being this, right? And we can factor it out into something that looks like this. And since 0 is not in our domain, 2x cannot be 0. Okay, so we can just factor that out. We're left with the fact that sine of x squared equals 1. So x squared is pi over 2 or 5 pi over 2, considering all the values that could be in our domain. And therefore, x could be just these two values, okay? And to actually determine their nature, so what sort of turning points they are, it would have to substitute these points, right? Substitute these points into the second derivative of f, right? To find out if it's a local maximum or a local minimum, right? Or an inflection point like this, right? But we don't have enough space on the slide to actually do that. If you did that, then you would find that these points are points of inflection, okay? So points like these. And that the other critical point is the endpoint of the interval, right? Which is x equals 2 root pi. And it's also the global maximum across the interval that we're given, okay? An easy way to do this with Maple, right, is to use this package, right? If you type in this command with the student calculus 1, then it basically imports a bunch of these functions that it can do for you, right? And one of them is the function, where is it? Critical points. Very useful, right? You put in your function, f, and you put in the interval across which you want to use it, right? And it outputs any possible critical point across that interval, right? So that's points where the derivative is 0, it's points where the derivative is undefined, and it's the endpoints as well, okay? So very useful command that you might want to use in your final exam. All right. Now, part B of the question was explain why f is invertible, so why f has an inverse, right? And state the domain of this inverse and find the inverse of 5 pi on 2, okay? So let's find out how we do this. We have to, first of all, justify why f has an inverse, right? So if you recall, that means that f has to be either increasing or decreasing across its domain, right? It can't be it can't be all wibbly wobbly, right? Like this, because otherwise the inverse will not actually be able to map certain y values to a corresponding x value, okay? So we have to show that it's either increasing or decreasing. Here's our derivative, right? And noting that a sine of x squared is always smaller than or equal to 1, right? 2x would always be larger than or equal to 2x times sine of x squared. So one subtracted from the other would actually always be positive, okay? And that means our derivative is always positive. Or, okay, strictly non-negative, okay? Not always positive, but non-negative. And that does imply that our function f is increasing, okay? And from before, you'll recall that the range, the domain of our inverse is just the range of our function, okay? So to find the range of our function, we find the minimum and maximum, and if you do that, you do actually get 1 and 4 pi plus 1, right? And that must be our domain for the inverse. Now, what was the last part of the question for this B? It was find the value of the inverse function at 5 pi on 2. Okay, so this is kind of tricky, okay, because obviously we're not going to be able to find an explicit expression for f inverse f, right? It's going to be very messy. Honestly, I don't even know how I'd do it, but there's a reason they gave us 5 pi on 2 for this question, and it's because if you notice, cosine of 5 pi on 2 is 0, okay? And if you think about it hard enough, then if we put in root 5 pi on 2 into our function, right, this part will square that value and we will just get 5 pi on 2. And this part would just go to 0, right? Because you would get cosine of 5 pi on 2, which becomes 0. So you're adding 5 pi on 2 plus 0, and that's exactly what we want, right? So the way you would actually articulate this in your solution is say, because cosine of 5 pi on 2 is 0, if you substitute this value into the function, right, you get 5 pi on 2. So if you just reverse that, the value of the inverse function at 5 pi on 2 must be this, right? In order to get this output, you have to have this input. That's what the inverse function is telling us. All right, and the last part of the question, where is this inverse differentiable, okay? So this is where we're actually coming back to this identity about the derivative of the inverse, okay? So let's have a look. Using the inverse function theorem, this is what it looks like, okay? So the derivative of our inverse is this fraction, okay? And we're looking for points where it does not exist, right? Where it's not, where the derivative of this inverse is not defined. And obviously that'll happen when this takes on the form 1 over 0, right? So basically we're looking for points where this denominator is 0, okay? And this basically happens when f of minus 1, okay, is, what were our values for when the derivative is 0? We found them when we were looking at the stationary points, right? So the derivative is 0 when x takes on these values, okay? So because we're putting f minus 1 into the derivative, we want to look for values where f of minus 1 is those surds that we got before, right? So root 2 pi on 2, and the other one was root 10 pi on 2, okay? And if you fiddle around, you will find that this is satisfied when x equals these values, okay? And that's the values when this denominator becomes 0, and hence our fraction is 1 over 0, and hence our derivative is not defined. So our derivative is defined where on the domain of our inverse that doesn't include these 2 points, okay? And that's our answer. Any questions so far about how we tackle that question? All right. Now, on to something completely different, which is curve sketching, okay? So graphing a particular function that we're given. from high school, you'll remember vertical and horizontal asymptotes, okay? So an easy one is, a hyperbola that looks like this, right? It has these two asymptotes. They go horizontal and vertical. But if you plotted some more complicated functions, you will have seen hyperbola that look like this, for instance, right? Where it looks like they have an asymptote that actually goes horizontally, okay? And this is basically formalization of what that means, okay? So if you have those two real numbers, a and b, right? They can define a straight line, okay? That'll be our oblique asymptote. And this oblique asymptote is an asymptote for function f if this is satisfied, right? And what this means is that here's our function, right? And say we're proposing that it has this oblique asymptote, right? This straight line. If that straight line is indeed an asymptote of this function, then you should expect that it gets closer and closer to that line, right? So this difference in the value between the function and the line should get smaller and smaller. And that difference is actually this expression here, right? You want that difference to go to 0, right? And so that's why that's our criteria for the function having an oblique asymptote, okay? All right, now, how can we apply this? We get this function 3x squared minus 4 over x plus 2, okay? So when we sketch a function like this, we want to have all the main aspects of the function conveyed in the graph, okay? So that includes the intercepts. I just misspelled intercepts. We need the intercepts, we need the asymptotes, and the oblique asymptotes if there are any, okay? And if it's a complex looking hyperbola like what we're given, that's a pretty good sign that there's going to be some oblique asymptotes, okay? So let's find the intersections first. So intersection with the y-axis, okay, is going to happen at whatever value you get when you substitute 0 into the function. So that's, 0 minus 4 over 0 plus 2, right? Which equals, obviously, minus 2. So our x-intercept occurs at y equals minus 2, right? And for our y-intercept, you do actually have to solve this quadratic, but it's not too hard. You get these two values, plus or minus 2 over root 3, okay? Now, there's also going to be a vertical asymptote, as you can see, right, from the denominator here. That denominator is going to become 0 when x equals minus 2, right? So that's going to be a vertical asymptote that we have. And finally, there is also going to be an oblique asymptote, okay? How we find that is we try to put the function into a form that looks like, so here's our function, right? We want to put it into a form that looks like a line, right? That'll be our asymptote, plus some function g of x that goes to 0, okay? That's how we actually determine our oblique asymptote, right? Because if this function g of x goes to 0, then our function f will get closer and closer to the value of this line as x goes to infinity, which makes it an asymptote, okay? So this is some high school algebra. We're trying to do some long division, right? To actually put it into this form. Oh boy. If you recall how to do this, you multiply the part that you're dividing to match up with the coefficients and the powers of the top part. But what you end up with is this expression, right? We've got, as we wanted, a line, right? A linear polynomial plus some function that goes to 0, right? It's got a constant at the top and a polynomial at the top, at the bottom, so it's obviously going to go to 0 as x goes to infinity, okay? So, what do we know about this graph? We've got the intercepts, we've got a vertical asymptote, and we've got an oblique asymptote, okay? So we could try drawing a crude graph of what this would look like, okay? So minus 2 This is going to be our vertical asymptote, okay? And our oblique asymptote 3x minus 6 is going to look something like this. I did make this a bit big, but what the function will look like is like this, right? It's like you took a regular hyperbola 1 on x and you kind of deformed its asymptotes to look like that, okay? And that's what it would look like. That's how you'd graph it. Obviously, you'd also label the intercepts, make it nice and neat, not sloppy like I have, but that's the basic idea of it. Once you have the asymptotes, then it's much easier to draw. All right, now onto something else. We've got polar coordinates, okay? So this might be something you haven't done in high school, and it's basically a different way to define points on the plane, okay? So usually how we describe a point on the plane is we have its horizontal coordinate and we have its vertical coordinate, okay? And that defines some point on the plane, one point, okay? Another way to define this point, okay, is say I were to draw a line from it to the origin. You look at the angle that that line makes with the x-axis and you look at the length of the line, okay? So basically what this is telling us, if you get the polar coordinates r equals 5 and theta equals pi on 3, right? What this is telling us is that to get to that point, you have to stand at the origin and turn pi on 3 radians anti-clockwise, and then walk forward 5 units to get to this point, right? That's what the polar coordinates are telling us, okay? And if you think about it, it's actually pretty easy to convert from polar coordinates to Cartesian coordinates, right? Because if you project this, then what you end up with is just a right triangle, right? And we remember from trigonometry that if the length of this is r and this angle is theta, then this length will be r sine theta, and this length will be r cos theta. So that vertical component is our y, and this horizontal component is our x, right? And that's exactly what we have here, okay? X equals r cos theta, y equals r sine theta. All right, now onto an actual question about this. So we're asked to find the gradient dy on dx of r equals sine 2 theta of this curve, defined by r equals 6 sine 2 theta, and we're asked to find the gradient at this point, right, where theta equals pi on 6, right? So when it's written out like this, it's really kind of unclear what the curve is going to look like, right? Because you're going to start at the x-axis, right, and your r value is going to be going all over the place, and you're going to be rotating, you're going to end up with some flower shape, okay? But basically, we want to break this down into the individual x and y components to actually find this gradient dy on dx. So from this result that we have up here, y is just r sine theta, and that equals to 6 sine 2 theta multiplied by sine theta. And x, likewise, is just r cos theta, which is equal to 6 sine 2 theta cos theta. Okay. Now, the usual way where we find the derivative of a graph is, you know, having some expression for y in terms of x, right? And then taking the derivative of it in the usual sense. But in this case, it's actually going to be very hard, as you can probably tell, to actually find an expression for y in terms of x, right? They're both in terms of theta. You'd have to do a bunch of rearranging, right? And it would just be too hard. Now, the tricky way of doing this is by realizing that this fraction dy on dx is equal to this more complicated looking fraction, dy on d theta over dx on d theta. All right? And basically what this is telling us is that to find the derivative of the graph at this point that we're given, we find the derivative of y with respect to theta, and we divide it by the derivative of x with respect to theta, right? We can treat these values x and y as functions of theta because we've got these expressions. So let's just take the derivative with respect to theta then, okay? So our y becomes, if I actually take the derivative correctly, I'm not going to write out the entire calculation. I'm sure you all know how to take derivatives. I do have the actual values in here somewhere. So dy on d theta becomes 12 cosine 2 theta sine theta plus 6 sine 2 theta cos theta, which ends up being 15 on 2 at theta equals pi on 6. Okay, so at the point that we're interested in. And the derivative of x with respect to theta ends up being 12 cosine 2 theta cos theta minus 6 sine 2 theta sine theta, which ends up being 3 root 3 on 2 at pi on 6. So our fraction dy on dx is this over this, right? So let's substitute them in. 15 on 2 divided by 3 root 3 on 2, right? And that's equal to 15 over 3 root 3, 5 on root 3, 5 root 3 over 3. Okay, that's our derivative. So the key idea that you should get from this question is that you can do this, perform this manipulation to turn the derivative into two derivatives divided by each other, right? If you have y and x described in terms of the same parameter, okay? In this case, it was theta. All right, now onto a completely different topic, integration, okay? So, integration, as you recall from high school, is sort of like the reverse of taking the derivative, right? Another way of describing it is that the integral of a function describes the area under the graph of that function from particular points A and B. Okay, that's the integral. And we have some identities about the integral that are actually particularly important. They're called the fundamental theorems of calculus. Okay, so you can tell they're very important. And the first one tells us that if you have this function that's defined as the integral, that should be a different parameter, t dt. If you have a function that's defined as the integral of some function from a constant 2x, right? So as you change x here, the bound is actually what changes, right? Then the derivative of this big F function will be whatever is just inside the integral. Okay, so that's why people say that the derivative is kind of the opposite of the integral, because if you take the derivative of something that's under an integral sign, then you actually end up with just whatever was under that integral sign. Okay. Oh, sorry, not plus c. What am I doing? All right. Any questions about this so far? Fundamental theorem calculus. All good? Any questions about the previous parts?
For the week of
Yeah.
quickly highlight how in the world you expand 3x cubed minus 4 to 3x cubed plus 6x and so on.
Okay. So yeah. So what we're doing here is we're just trying to break down this into multiples of x plus 2, right? Because we're trying to factor out x plus 2 from that top expression, okay? So if we've got a 3x squared, right, in that top expression, right, then the closest that we can get to 3x squared with a multiple of x plus 2 is 3x times x plus 2, right? And that gives us 3x squared plus 6x, okay? So that's why we have this 3x squared plus 6x in the top here, right? Because when you factor out x plus 2 from that, you get 3x, a nice, normal, linear expression, right? But obviously we have to keep the top the same value, so now we have this minus 6x lurking around, right? Because we have to subtract what we added on, okay? So now we have to try to turn this minus 6x into a multiple of x plus 2 as well. So maybe it'll make it more clear if I do it here. So we've got, right, over x plus 2, right? So first we want to change the top expression so that this first term is some multiple of x plus 2, right? And the way we do it is we change it to look like this: 3x squared plus 6x, right? This expression is a multiple of x plus 2, right? But to keep the fraction the same, we have to subtract the 6x that we added on and keep the minus 4, right? And now we want to change this term to be some multiple of x plus 2 as well, right? So the way we do that is we keep our 3x squared plus 6x, right? And we change it to be minus 6x. We multiplied it by minus 6, right? So this would be minus 12, right? And this is also a multiple of x plus 2 now, okay? So so basically what I'm doing is I'm turning this minus 6x, right, this term, into a multiple of x plus 2. And the multiple of x plus 2 that I chose was this one, right? So I can rewrite it as the multiple if you want. Multiply, so we're adding minus 6 times x plus 2, right? And conveniently, if you do that, if you expand that out, the first term actually becomes minus 6x, right? Minus 6x minus 12 is what we get, right? And then we do have to add that 12 back on because we didn't have that minus 12 before, and we still have a minus 4 lurking around, right? Unless I'm mistaken. I may have made some error in calculation along the way. Oh no, it's fine. Okay, so here we have an equivalent fraction, and now we can actually just divide through, right? This part, when divided by x plus 2, would give us 3x, right? This part, when divided by x plus 2, would give us minus 6, right? And this part, you can't divide by x plus 2 no matter what you do. So we're just going to leave that as 8 over x plus 2, right? So yeah, basically all that entire process was just to get this function rewritten as a linear term plus some, fraction. Yeah, yeah.
Can we just do the first bit with long division? Would that still work or no?
Yeah, long division, right? As long as you have it rewritten as as long as you have the top rewritten as some multiple of x plus 2 plus some remainder, okay? That's all you're looking for. If you want to practice this more, it's just called polynomial long division, right? If you get a knack for that, then it's easier later on, okay? Okay, what were we up to? All right. The fundamental theorem of calculus. All right. So, as I was saying, the derivative is like the opposite of the integral in that if you take the derivative of a function that's defined with an integral, you just get what was under the integral sign in the first place, okay? These two kind of cancel each other out. All right. Now, the second fundamental theorem of calculus tells us that if you have an integral from some bounds, right, then it's evaluated by taking the difference between two antiderivatives, okay? So in this case, f is defined to be some function such that derivative of this big F is f of x, okay? That's what an antiderivative means, and that's what you use to calculate the value of an integral like this, okay? All right. Now, we've got this question, right? This is a function defined in terms of x, right? Except what x changes is actually the bound of the integral here, okay? And we're asked to find the derivative of this with respect to x. So, how do we do this, okay? We are given a useful identity here. It may look intimidating at first, but once you get the hang of it, it's not actually that complicated. What's happening here is that it's just, we're kind of applying the chain rule, basically, right, to a more complicated function. So if we actually use this identity that we're given, this is equal to our antiderivative evaluated at the top bound minus the antiderivative evaluated at that bottom bound. Now what we find is that the derivative of this part, right, will just be 0 because this is just a value, it's a constant, right? So this vanishes, right? And all we're left with is a derivative of this, right? And it's a function inside a function. To find the derivative of that, we just apply the chain rule, okay? And what we get is that the answer is the derivative of this hyperbolic sine function, right, multiplied by the derivative of f evaluated at the hyperbolic sine function of x, okay? And from the way that we defined it, f is defined by an integral. This is our function f, right? Our function f is just the integral from 0 to x of this funky looking expression here, cosine of t over 1 plus t squared dt. And if we take the derivative of this, then we just end up with whatever was inside the integral sign, okay? So what this ends up being is that we're taking the derivative of the hyperbolic sine function, right? And also evaluating this expression, right? Cosine of x over 1 plus x squared at sine h of x, okay? And it does look a bit messy at first, but now we do have an explicit expression for the derivative. So what we obtain, right, is cosine of hyperbolic sine of x, right, over root 1 plus the square of hyperbolic sine of x multiplied by hyperbolic cosine of x minus this term, which just goes to 0, as we've said, right? This is equivalent to this term, which has got differentiated into 0, okay? And when you simplify this, this does actually just become the cosine of the hyperbolic sine of x, because we used this identity, right? Hyperbolic sine is some functions that we'll study more in depth later on, but for now, we just need to know a couple identities about them, and this is one of them, okay? So the main idea behind this is that we applied the fact that the derivative is just the opposite of the integral, okay? When we took the derivative of this function that was defined as an integral from 0 to x of something, then we just got back our something, the thing that was underneath the integral sign, okay? And here in the notes, we do have a more general expression for what you actually end up with when you take these sort of derivatives, okay? So this is f evaluated at u of x multiplied by the derivative of u at x minus f evaluated at L of x multiplied by the derivative of L evaluated at x, okay? That dt should not be there. And again, this just comes from substituting our function bounds into this expression that we got from the fundamental theorem of calculus, okay? That's where it comes from. And then you take the derivative and you end up just with this from the chain rule, okay? Any questions about that part? Are you talking about this question in particular?
Yeah, because since it's just sine h x minus f0, why don't you just keep sine h f? Why don't you just divide that? Is it because it's in the f prime bracket?
So which part are you confused about? Taking the derivative of this bracket?
Taking like the special state where you take sine hx and then you take the derivative of sine hx.
Oh, right. Okay. So what I did here is that I defined this big F, right, to be this function. Okay. I defined it to be that. Okay. And if you notice, this expression that we got given is F, but where x was replaced with hyperbolic sine of x. Okay, that's what happened here, right? This expression that we got given here is the same as our expression for f, right? But we substituted in hyperbolic sine of x. Okay, so that actually made it easier for us because now we could replace this expression, right? This expression with this expression, okay?
Could you expand that?
Okay, so I'll write it out for you because the page is getting a bit messy, okay? So here is our question, right? Find the derivative of, well, a bit messy. Derivative of this function, and our function is defined to be the integral from 0 to hyperbolic sine of x of, was it cosine t over 1 plus t squared? Yep, dt. Right? This is what we're looking for. And what I did was I said, let this function f of x equal to this expression, okay, the integral from 0 to x of this t stuff, okay? And what we've noticed is that this expression that we got given is equivalent to f evaluated at hyperbolic sine of x, okay? Do you see that? Yeah? So, when we take the derivative of a function that's inside a function, right, what happens? What rule do we apply of differentiation? It's the chain rule, right? So chain rule is when we're trying to take the derivative of two nested functions, remember? And that's what we have here. We've got this function f, and inside it is this function sine h, right? Yeah. Okay. Does that clarify what we did there? Yeah. Okay. And that's what the expression that we get, right? Yeah. Okay. Moving on. Okay. We've got a technique for integration. All right. It's called integration by parts, and it's used when you have when you're integrating a product of two functions. Okay, u and dv. Okay. And the way that you actually find this, right? The way that you would derive this algebraically is you start with the product rule. So everyone remembers that the derivative of two functions multiplied together is what? It's one function multiplied by the derivative of the other, right? Plus the other function multiplied by the derivative of the first, right? Everyone recognizes that? Now, what we do now is we take the integral of both sides, okay? And what happens here is that the integral and the derivative cancel out, okay, on this side. So we're just left with uv. And on this side, we've got these integrals, right, of the products of our two functions, okay? And if you rearrange it, you do actually get this identity, right? All you're doing is you're subtracting one of them from both sides. Okay, so if you want to leave u v dash dx on its own, then you would subtract this part from both sides, and you'd be left with the fact that uv dash dx, or the integral of that, is equal to uv minus integral of v u dash dx. Okay, and that's just a rewritten version of what we have here. Okay, and how do we apply this rule? Okay, the trickiest part when we do integration by parts is actually figuring out how we split up the function that we're integrating, right? We have to split it up into a u component and a dv component. Usually what we'll try to do is we let our u be something that's hard to integrate, because in our right hand side expression we're actually not integrating u at all. And v, the second part, dv, it'll be something that's easy to integrate, because we will have to integrate dv to become v, right? And substitute that in for our integral expression, okay? So let's actually go through an example of how to apply this theorem. Use integration by parts to evaluate the integral from 0 to root 3 of the inverse tangent of x. Okay. We use something called the Liate rule, okay? L-I-A-T-E, right? There's different versions of it, but they all basically have the same idea, right? And it's a guide for which functions, for how to break up the function that you're integrating into your u and dv, right? And what Liate stands for is log inverse trig algebraic trig and exponents. So what this means is that when you are choosing the component of your function to be the u part of your integrand, you'll want to go down this list. Start with a logarithm, then go to inverse trig, then go to algebraic, because the first one that you actually encounter, first one out of these that you encounter as you go down, will be the optimal choice for your u, because this basically is a list of different types of expressions that are hard to integrate. Log expressions are hard to integrate. Inverse trig expressions are hard to integrate, and that's why you want to choose them to be your u component. Now, if we apply this to the actual integral that we're given, right, we do encounter an inverse trig component, and that's our function itself, right? So we want to break down our expression, inverse tan of x, into the product of inverse tan of x times something, okay? And the way that we've done this in a bit of a cheeky manner is broken it down into 1 times inverse tan of x, okay? So we've chosen our u to be this inverse tan, and that means the derivative, the du that we're going to be substituting into our expression is just 1 over 1 plus x squared. And we've chosen our dv to just be 1, okay? Or 1 dx. And that means that our v component, after integrating, would just be x, okay? And now finally, we can substitute it into our formula for integration by parts, okay? These slides do actually skip a couple steps because they evaluate it at the bounds immediately. But if we do want to substitute it in carefully, we get that u dv equals uv minus the integral of v du, okay? So the integral of inverse tan of x times 1 times dx, because we chose now dv to be 1, is equal to uv. What's our u? Inverse tan of x. What's our v? X. X tan minus 1 of x minus the integral of, what's our v? X. What's our du? 1 over 1 plus x squared. Okay, that's a derivative of inverse tan of x. And now we've got a separate, different looking expression for the same integral, okay? These two are equal. And then, once you have this, you can actually evaluate it at the bounds, right? From 0 to root 3 will have the same effect on this side, right? Evaluate this from 0 to root 3 and evaluate this from 0 to root 3. And that's what we have here in this expression in the slides, right? X times tan inverse of x, evaluate from 0 to root 3, right? Minus this integral from 0 to root 3 of x over 1 plus x squared, right? And this expression is much easier to integrate. It's just, you know, a linear over a quadratic. That will give us a log expression. This is what it gives us, right? And this is much easier to evaluate. If you do sub in these values into what we have in the brackets here, you end up getting negative half natural log of 4, okay? Which simplifies to pi root 3 on 3 minus natural log of 2. Any questions about that? How to apply integration by parts?
Just to clarify, what we're looking at is the right-hand side, right?
Yeah, this is the right-hand side of this substitution. Okay, so when you apply the integration by parts, you want to pick a u and dv so that this left-hand side becomes the thing that you want to integrate. And then you substitute in the u, the v, the du into the right-hand side to get a different expression for the same integral, right? And that usually, hopefully, helps you integrate it. Okay, now, let's talk about divergence and convergence, okay? Just some terminology. If a function diverges, as x goes to infinity, that means the function goes to infinity, okay? If a function converges as x goes to infinity, that means the function approaches some value, okay? And here we're talking about whether integrals converge or diverge, right? So, the idea that we're conveying here is similar to what Angie talked about when she talked about the sandwich theorem, okay? So, we're given, suppose that f and g are integrable functions, and that f of x is always between 0 and g of x, right? So, if we want to draw this out, our g of x looks like something like this, right? And our f of x has to look something like this. It's between the x-axis and g of x, right? This is g of x, and this is f of x. And what it's telling us, if the integral from a to infinity of g of x converges, so is finite, then the integral of f of x from a to infinity also has to be finite, also has to converge. And this is, you know, it's kind of common sense when you think about it, right? If the area under g of x from some point A taken out to infinity is, whoops, I don't know where that went. If the area under g of x from A to infinity, I don't know where my drawings are going. Maybe. Oh, really? Well, how am I supposed to scribble? Oh, okay, I'll scribble around. Yeah. Okay, hopefully that conveys the idea. If the area under g of x from A to infinity is finite, then this area under f of x from A to infinity, which is strictly smaller than that first area, also has to be finite, right? And that's what it says, right? If this large value converges, then this smaller value must also converge. This second part is kind of the opposite, right? So if I redraw my f of x and g of x, hello? So if I have an f of x that goes like this, right? Clearly f of x diverges here, right? Because the area would go to infinity. And g of x is larger than f of x, then the area under g of x would also go to infinity, right? Because it's strictly larger than the area under f of x. And this is what it says, right? If this smaller value goes to infinity, then this larger value must also go to infinity, okay? And let's apply this comparison test to a question. Determine whether the improper integral k, which is from 1 to infinity of 1 plus sine of x over 3x squared, converges or diverges. All right? And the idea here is that we're going to find a function, right, that is larger than this function that we're integrating. So an integral that is larger, well, I guess in this case it would be g of x. G of x. And if we can show that this converges, then we can show that this converges as well, right? So let's give it a go. What we know is that this top part, 1 plus sine of x, it's always going to be less than 2, right? Because sine of x is always less than 1, or less than or equal to 1. So that top part is going to be less than or equal to 2, okay? So here we've got a function that's strictly larger than or equal to our original integral, right? Which is 2 over 3x squared, right? And the integral that we end up with is this particular integral here, okay? 1 over x squared. And we're trying to check if this converges or diverges. Now, what we apply to actually find this out is something called the p-test, okay? These integrals, where it's 1 over x to some power, have a neat little rule, have a neat little rule to check if they go to infinity or actually converge to some amount. And it's called the p-test, right? If p is larger than 1, then the integral converges, right? So converges if p is larger than 1. And if it's smaller than or equal to 1, then it diverges. So it goes to infinity, okay? And in our case, we do have a p-form integral, okay? 1 over x squared. In this case, our p is 2, which is larger than 1, right? So our particular integral converges. So this integral that we found that's larger than our original integral converges. So this one must converge as well. Therefore, k converges since it is less than or equal to an already converging integral. Any questions about that? Yeah.
The p integral, can you just apply that to just the beginning one since it has an x squared at the bottom? Or you can't?
No, you can't, because it's not of p form, right? The p-test only applies to functions that look like this, integrals that look like this, right? Sorry, not 0. 1 over x to the p of some sort, right? I guess you could have a constant here because that would just multiply whatever your value is. But the point is that you can't have anything special up at the top, right? That's when you can apply the p-test.
So, because if we do, could it falsely give us like diverge and converge, or it's just a rule? So
yeah, so the problem here is that, say for instance, you had a function that looked like this, right? 1 to infinity, nope. And at the top you had some linear term, for instance, right? And at the bottom you had x squared, right? If you apply the p-test, you would say, hey, 2 is larger than 1, it must converge. But in this case, because you've got that linear term at the top, it actually grows a bit bigger than 1 over x squared, and it wouldn't actually converge, right? This one would not converge. That's why, yeah, we always look for a form like this to apply the p-test. Okay, and on to the next topic, which is logs and exponentials, right? And how we can apply them. So, I'm not going to give away the solution yet. Suppose that y equals x to the power of sine of x, right? And we're asked to find the derivative of y with respect to x. The straightforward way of doing this is just applying chain rule, right? This expression here is of the form f of g of x. Oh, sorry. Actually, correction, no, it is not. And that's why we need to apply this logarithm trick to actually find out what this will be, okay? So, the solution to doing this is just taking the logarithm of both sides. So, on this side, we get the logarithm of y, you know, ln y. And on this other side, we get a much simpler expression, sine of x times natural log of x, right? Much easier to differentiate. And then when we differentiate it, the left-hand side becomes 1 over y times the derivative of y with respect to x, right? dy dx, which is the quantity we're looking for. And on the right-hand side, we get this complicated-looking expression here, right? And we're trying to isolate this dy dx term, so we multiply through by y, and then we substitute in what y actually was, which is x to the power of sine of x. And this is exactly what we get, okay? dy over dx is x to the power of sine of x times cosine of x, natural log of x plus sine x over x, okay? Very complicated looking expression, but we got it pretty easily by applying this trick of implicit differentiation, okay? Taking the logarithm of both sides. All right, and for our final topic this evening is hyperbolic functions, okay? This is something you probably did not see in high school, right? Hyperbolic cosine, hyperbolic sine. They're defined quite differently from sine and cosine that we're used to. But they do follow some of the same identities. They do follow some of the same identities, right? So one thing you'll note is that if you add these two expressions together, our definition for hyperbolic sine and hyperbolic cosine, you get 1/2 of e to the x plus e to the minus x plus e to the x minus e to the minus x, okay? And that ends up being just e to the x, right? This is what you get when you add hyperbolic sine plus hyperbolic cosine. And we saw, and we saw from earlier as well that 1 plus hyperbolic, 1 plus hyperbolic sine squared is equal to the square of hyperbolic cosine, right? Just like with regular trig, okay? So that's why I guess they're called the hyperbolic trigonometric functions, because they share some of the properties of the regular ones. And let's do a question involving them, okay? We're asked to calculate this integral with the scary looking hyperbolic functions in the denominator. But if you remember our identity from before, they do actually simplify into something much neater. They simplify to just become 1 over e to the x, okay? And it's pretty easy to take the integral of 1 over e to the x, that's just e to the minus x, right? And when you evaluate that, you just get 2/3. Any questions about that? No? And that brings us to the end of the presentation. Everyone in the auditorium, I hope you enjoyed, hope you learned something. Everyone on stream or watching this later on, I hope this helped. And good luck in your exams, guys. Come to camp. Math camp.